me, then I would like to open our Monday seminar. This time we will stay at home, so to say, because the authors of the presentation all belong to ÚFAL. As far as I understand, David Mareček is the leader of the group, and he will introduce the other speakers with his first or second slide. And I must say that I'm very happy to see the title and the abstract, because I do hope that some secret of the black box will be open during the talk. So please start, David.
Okay, thank you for the introduction. So the topic of today's talk is hidden in the layers, interpretation of neural networks for natural language processing. This work is made under, or was made in the last 3 years at ÚFAL, and it's under the Gotcha project, Gotcha grant, which is called Linguistic Structure Representation in Deep Networks. The abbreviation is LSD. And so our team is me, Jindřich, Libovický, Rosa, Tomáš, Musil, and from the last beginning from the last year, from the previous year, we Tomasz Limisiewicz joined us. And so this talk will be given by me, Jindřich, Rosa, and Tomáš, Musil. So first, some introduction and motivation. So the goal of our project is you all know that the deep neural networks are very popular today, and they have rapidly become a central component in many NLP systems. And the problem is, or not the problem, but these networks are trained in end-to-end fashion. So these networks act like black boxes. So it's very hard to interpret what is happening inside during the processing of language. And because they don't have any explicit knowledge about linguistic abstractions compared to the 5 or 10 years ago, when we used parsing, tagging, and everything, all these subtasks for almost all NLP tasks. Today we don't use much these linguistic abstractions, and the goal of this project is to open this black box. So we would like to find out how these neural networks work inside. What are the emergent abstractions that we observe there? How we can interpret the internal representations there. And if we find any of emergent structures or abstractions there, we would like to compare them, whether how much these are similar to classical linguistic structures and abstractions. Like, for example, are there something like dependencies or dependency trees? Are there hidden something like part of speech tags or morphological categories, coreferences, and like semantic abstractions? So we would like to know this, what is happening, what is in these black boxes. So this is the goal. In our work, we mainly focus on the neural network architecture, which is called transformer. And in transformer, we analyze mainly the word embeddings, the contextual embeddings, and the self-attentions, which are joining connecting the individual embeddings, individual representations. So now this is the outline of this talk. So this talk will be rather several small studies on the different parts of different parts of neural analysis of different parts of neural networks. I will show generally some methods. Then Tomáš Musil will continue with analyzing word embeddings. Then there will be contextual embeddings. Jindřich Libovický will talk about a multilingual BERT model and its multilingual properties. Then Rosa will talk about the problem of memorization in the supervised probing. and then I will tell you something about how we can separate the lexical and syntactic features in the contextual representations of the BERT model. And then I will talk about the self-attentions mechanism and how these self-attentions are similar to syntactic labels or syntactic dependencies. So first, I will talk about neural machine translation transformer and whether we can extract the phrase trees from this model. And then I will tell something about the BERT model and how it captures dependency relations in individual self-attention heads. So first, generally about the methods, we can divide the methods into two categories: supervised, which is called probing, and unsupervised. In probing, we have neural networks. Imagine that we have some neural network, and we have a contextual representation of words, let's say, and we would like to find out what is hidden in this contextual representations. So we can train a supervised classifier that predicts linguistic features on top of the original neural network, and we do the training, but we fixed the parameters of the original neural networks, so we don't do any fine tuning. We only training this classifier, which is predicting the linguistic features, for example, part-to-speech tags or dependency relations or dependencies or anything. And if the accuracy of this probing classifier is high, we can assume that the linguistic features are somehow present, somehow hidden in the contextual representations. So this is the probing, and the disadvantages or some drawbacks of probing is that it requires data annotated for the studied property, and the problem is that it can only reveal the information that we have previously decided to look for. And we have to have the annotated data, and probably suppose that we have, for example, universal dependencies and part-of-speech tags there, and we do the probing, and we find out that, for example, in contextual representation, we have about 95% accuracy. So we can say, okay, so the part-of-speech tags, as they are annotated in the universal dependencies, are somehow included in the contextual representations, but maybe there exists a better part-to-speech tag set or better rules how to assign text to words, but we cannot probe for that because we don't know what it should be. So the supervised approach only like retroactively affirms the correctness of one conceptualization and design decision, but that's the problem. So on the other hand, the unsupervised methods, we don't need any data. So for example, you can do clustering or component analysis on the vector representations. We can do structural inductions from the self-attentions of the transformer, for example. And in this unsupervised method, we first analyze the features that emerge in the representation. So we analyze the main features. And only then we can try to map these features into existing linguistic abstractions. So we, in unsupervised method, we really find the main structure or the basic structure, the main features, and then we try to map it. The problem is the complicated evaluation because it's hard to it's always complicated to evaluate it on some existing data. So it's problematic in this way. Another issues with interpretation is words versus states, because we would like to analyze, for example, this representation, this contextual representation, or this word embedding, like this representation of a word. In word embeddings, we know that these are only the word as the respective positions are like they encode the words at the respective positions. Whereas the contextual embedding, because they are contextual, they can include any of the words from the sentence, and they, for example, the contextual representation as this position, it may include the word it, but it may include all the words, but maybe it doesn't include the word it much because it is a pronoun. Maybe it more likely it includes the word box, which is on the different place of the sentence. So when you want to predict, for example, part-of-speech tag of this representation, we don't know whether it is the representation, it is the contextual representation of the word it. It is like the contextual. What is contextual representation? It can be the representation of the whole sentence in some point of view. So that's the problematic thing, that any word, information from any word may be present at any of these contextual embeddings. Another problem is the difference between words and subwords, because the current neural network models typically operate on subword units. So these units are typically shorter than words, whereas the linguistic formalism as a part-of-speech text and dependency trees, all of these are annotated on words, of course. So these are problems how to compare the abstractions we get from the neural networks with the linguistic formalism we have like as annotated data. So there are we can say that there are three approaches how to deal with that problem. We can either modify the linguistic abstractions to apply to subwords. So we can, for example, automatically assign part-of-speech text to all the part-of-speech text to all the subwords, or we can transform the subwords to words for word representation. So when we get the representation from neural networks, like the representations for individual subwords, we can combine these representations, for example, summing or averaging these representations to get a representation, get the representation for the word. Or we can use a fully word-based approach when we train the model, the same model, but not on the subwords, but on the words. The problem here is that the model trained on words is not as good as the model trained on subwords. So we are no longer analyzing the best model. We are analyzing like similar model. This is not as best, but not as good. So these are the problems with words and subwords we have to deal with somehow. Okay, so that was the introduction, and let's go to the word embeddings, which will be presented by Tomáš, Musil. So I need to stop share.
Hello, everyone. Thank you, David, for the introduction. And now I will briefly speak about unsupervised methods for analyzing word embeddings. Okay. So word embedding is a vector that represents a word. It can be, for example, 100-dimensional vector, that is, each word will be associated with a list of 100 real numbers. They can be learned in an unsupervised way from large plain text corpora, or they can be learned as part of the task, for example, machine translation. And yeah, the words that appear in similar contexts usually have similar embeddings. And one general note about the representations and neural networks, the stronger neural network we have sort of above the embeddings, the less information about the words is actually in the embeddings themselves. So, for example, the word-to-vec model, which is sort of a neural network which only has the embedding layer and nothing else, if we conceptualize it as a neural network. In the Word-to-Vec model, all the information is stored in the embeddings. But then if we use a simple recurrent neural network, then there is less information in the embeddings. If we add the attention mechanism, even less, and with transformer, with all the attention layers, we see less linguistic information in the embeddings, presumably because the information is stored somewhere in the attention heads. And now, one of the methods of analyzing the word embeddings is the principal component analysis. That is a method that basically transforms the data in such a way that the first component is the direction in the data that explains the most variation of the data. The second principal component is the next one that explains the most variation after we've sort of squashed the first component, and so on. This is an example of such analysis. We have word embeddings learned by a neural machine translation model. And we have the principal components on one of the axes, and the other axis is part of speech categories, nouns, adjectives, and so on. And this is sort of a correlation matrix. So this means that in the first picture, the first PCA component strongly correlates with nouns and strongly negatively correlates with verbs. And we will see in the next slide a little bit more about what that means. But on this slide, it's important that one of the images is for embeddings from the encoder. The other is for the embeddings from the decoder. So it's actually two NMT models. One is from Czech to English, and the embeddings are Czech embeddings from the encoder. The other is from English to Czech, and the embeddings are Czech embeddings from the decoder. And you can see that the encoder and the decoder represents words in a different way. And here, this is a histogram of words along the first principal component for the encoder embeddings, I think. And it's actually 4 histograms for the 4 largest part of speech classes: verbs, noun, adjectives, and adverbs. And you see that the first principal component kind of separates verbs from the rest. Then the second principal component has an interesting distribution, and we will talk about that later. And then the third component, for example, sort of there are adjectives are sort of on the side, but let's go to this slide. Here we see the same thing, but this time it's two-dimensional plot of the first 2 principal components, and then for the second and third principal component. And you can see this little cluster of nouns that is clearly separated from the rest of the words. And if we take a sample from that cluster, we see that it contains almost exclusively named entities. So that's one thing that is important for the particular NMT model, named entities. Another example is an analysis of word embedding space learned by a model for sentiment analysis. This model was trained on the ČSFD film database. The data were user comments and ranking of the movies. It was a convolutional neural network. So the task is to for the network to read the comment and decide whether the comment was negative or positive. And the word embeddings in the first two principal components have this strange triangular shape, which is quite uncommon. You can see on the first side that this is like not a normal distribution. And if we sample words from this embedding space, we see that the horizontal axis actually represents polarity of the words, so with negative words on the left, such as stupidity and worse, and positive words on the right, such as magnificent, brilliant, and so on. And the vertical axis represents intensity of the words. So the words that are on the top are not very intense, words such as average or uninteresting. The words that are on the bottom are very intense, so for example, absolutely or biggest. So that explains the triangular shape, because words that are very positive or very negative are also intense. Safe. Yeah. Another example, this time for clustering, is clustering of word derivation. Here, each point actually represents a pair of word embeddings. These pairs of words were taken from the DeriNet derivational database. And you see that similar derivations form clusters together, even though the model, I think it's Word-to-Vec in this case, doesn't know anything about the morphology of the words. So it doesn't know that smutný and smutně are rather similar words. It only sees the usage of the words, and it clusters similar derivations together. And the last example is independent component analysis. This is a method that was actually mostly used in like signal processing. The prototypical example is the cocktail party problem, which is illustrated here. We have some people, in this case, person 1 and person 2, who are speaking. They are speaking both at the same time. And we also have the same number of microphones in the room. But every microphone is getting signal from all the persons mixed together. But because the microphones are at different places and the people are in different places, the mix in each microphone is also different. Now we only have the mixed signals, and what we want is to get the unmixed signal back. So this is actually done by finding non-Gaussian components in the data. And the principle is quite interesting, but I don't think I have enough time to explain it in detail. Anyway, when we apply this to word embeddings, we sort of presuppose that there are some features of the words that are mixed together in the embeddings, and we are trying to unmix them. And the result seems promising so far. So this is one example of the independent component. These are words that were sampled from words for which this particular independent component was higher than all the other independent components. Anyway, the technical details are not all that important. The important thing is that the independent component separated words that clearly have something semantic in common. In this case, these are words connected to law, justice, and things like that. But then there were other independent components that sort of mixed semantic and syntactic features together. So this is a component that only has verbs, but they are all connected with going somewhere, and they are all masculine and in past tense. So that's quite a specific category. Other independent components were more syntactic and less semantic. For example, this one, which shows adjectives in feminine singular form. Even other components show interesting syntactic or morphosyntactic subcategories, such as this component which separates feminine plural form, but for adjective, pronouns, and verbs. So in this case, we only had adjectives. In this case, we have adjective, pronouns, verbs, but they are all feminine plural. And then there are even components that separate some stylistic, I would say, features, such as this one, which contains a lot of words that appear in informal spoken language, and also a lot of second person verbs, which are also connected to direct speech. Yeah, so that's all the examples I have. And now Jindřich will tell you something about multilingual BERT.
All right. I hope you can hear me and that you can also see my screen. Yeah, and I'm going to talk about our study on multilingual BERT and other pre-trained multilingual representations that we recently published in Findings of EMNLP as a joint work with Alex Fraser here in Munich, where I am currently based. Well, what are the multilingual pre-trained representations? Multilingual BERT doesn't principally differ from the standard BERT. The only difference is that it is trained on 100 languages simultaneously, but there is no information about the language identity provided during the training. It's just text as any other. And even though it is trained in this sort of simplistic way, it reaches surprisingly good results when zero-shot transferring of the models. By zero-shot transferring, we mean a special way of training the model when we want to train a model, for instance, a classifier, on top of the multilingual representation. But we only have training data in some high resource language, for instance, English, but we want to use the model in a low resource language. So we train the model on a high resource language and then transfer the knowledge to the low resource language and use the low resource language at inference time. Well, this has various problems. One of those is that literature presents very inconsistent results on these tasks. Another problem is that if this approach doesn't work well, we can never be sure if this is a property of the multilingual representation, or if we sort of overfit it to the parent language on the high resource language. And on the other hand, if it works well, we can't be sure if it is due to the model or due to the underlying pre-trained representation. So in order to better evaluate the representations directly, and specifically their semantic properties, we wanted to avoid the zero-shot transfer and use the representations directly. We do it on several probing tasks. We start with language identification. We do parallel sentence retrieval, word alignment on parallel data, and we also did machine translation quality estimation that I'm going to skip in today's presentation. We worked with multilingual BERT that was introduced jointly with the original BERT 2 years ago. A small version of the model that was created from the original multilingual BERT by knowledge distillation. An XML Roberta model that was trained last year by Facebook Research, and they claim that the original multilingual BERT was undertrained, and they trained the same model on much larger data and get much better representation quality. And finally, we also probe fine-tuned multilingual BERT from the Unify model. It was a work of Milan Straka and his students. And at this dependency parser trained for all UD languages at the same time, and they fine-tuned the multilingual BERT representation for it. So the hope is that such representation might have become more language neutral by this fine-tuning. We started with language identity. We trained a probing classifier, and to our surprise, we found out that we can train better classifiers than the state-of-the-art classifiers using fast text. So the natural question is, how can the representation be language neutral if the language identity is so well represented inside the representation? We also try to have a look at how the average representations, average embeddings in the languages look like. And we found out that they tend to cluster according to phylogenetic language families. And if we quantitatively compare the hierarchical clustering of the representations with the language families as they are in the WALS data set, we find out that the multilingual BERT does a pretty good job on recovering the language families. And also that the XMLR, which is supposed to be more language neutral, does not perform so well on that task. So from these preliminary experiments, we came to a hypothesis that language identity can be represented as a sort of constant offset in the vector space of the embedding, and that might make the representations more language neutral by subtracting the mean of other specific languages and sort of centering the representation. And when we try it on the language identification, it works. With the centered representations, we can get much worse accuracy than without the centering. Also, when we have a look how it performs for the various layers of the multilingual BERT, we can see that it's a large drop for all layers, and also that the XMLR model that should be more language neutral indeed gets worse accuracy and language identification, but still highly over 90%. we tried to confirm our hypothesis on sentence retrieval. We shuffled parallel data from the WMT14 evaluation campaign and tried to retrieve the nearest neighbors based on the cosine distance. And the results sort of confirm our hypothesis. When we center the representation, we can get almost 6% improvement in the retrieval accuracy. Also, you can notice that when we compare that with static multilingual embeddings, that means word embeddings that are not contextualized at all, which are, on the other hand, explicitly trained for language neutrality, the results are much worse. But on the other hand, if we train an explicit projection between the embeddings in various languages, the accuracy is even better, which suggests that there can be more things done than just shifting the embeddings one way or another to make them more language independent. And this is also an interesting result. The UDFI model without any changes performs quite poorly. And we hypothesized that this might be because the fine-tuning for dependency parsing sort of removed the semantic information from the embeddings, because that was not necessarily needed for the task it was fine-tuned on. Yeah, we'll skip that. And now to word alignment. It's another task we probed the multilingual representations on. And we formulated the word alignment as finding a minimum weighted edge cover in a bipartite graph with edges weighted by the cosine distance of the embeddings of the words in the two languages. And to our surprise, we matched the performance of the statistical aligners trained on 1 million parallel sentences without using any parallel data at all. Also, our results are much better than using static word embeddings, which shows that the role of context is very important in word embeddings. And this result also indirectly confirms our hypothesis about a constant shift of the languages, because when we do the bipartite graph and do the matching, then the constant offset sort of zeroes out when and becomes a constant that does not change the graph matching. So this is what we found out about language neutrality, or sort of semantic language neutrality of the embeddings. The pre-trained multilingual representations are not much language neutral, as it may seem from the experiments with zero-shot transfer. And it's mainly because the language identity is very useful feature during the pre-training. Also, we found out that language-specific centering of the representation is a simple and good unsupervised way of improving the language neutrality. Although training explicit projection between the representation is much better, but it requires parallel data. As a nice side effect, we reached state-of-the-art results for language identification and word alignment. There are indeed many remaining open questions. The most important ones are whether we can match the explicit projection using some unsupervised methods, and also how can we make the representation language neutral sort of by default without doing some explicit reprocessing as we did in this work. And this is all for me now, and the next speaker is Rudolf.
Thank you. So try to share. Okay, I hope you see my presentation. I have just a small topic within the whole problem of interpreting the trained models. And what I deal with in my short input is actually a problem of the probing method that we thought is a bit understudied. As David introduced in the beginning, probing is a typical approach of trying to discern what kind of linguistic features can be extracted from some representation. So for example, we take contextual embeddings and we train a probing classifier, and we observe that the probing classifier can predict a label such as part of speech based on the contextual embedding. And the usual explanation in research and what you actually want to posit is that this shows that the probe model, so these contextual embeddings, do capture something like part of speech within their contextual embeddings, but there is a risk that this can be a misinterpretation, that in fact the situation can be that the representations just capture the identity of the words, and your probing classifier only memorizes the part of speech for some individual words. So you're only showing that the classifier can remember part of speech for individual words, and that your representation does encode the word identity, but you do not show that the neural network itself uses some kind of abstraction which would be similar to part of speech. So this is kind of a risk that should be addressed and often is unaddressed. And so this looks like the typical problem of overtraining. And the solution should be something like, yeah, so let's use a different set of training words and testing words so that we eliminate this problem. So we only probe for part of speech of words that we did not see in training. Which in fact is the idea of the solution to use, but there is some problem which is new with these contextual representation, which is that we need to use the full sentences to compute the contextual representations, and of course the sentences will overlap in words, and it is quite possible that information about the surrounding words might be encoded within the contextual embeddings for the other words. We still suggest to use such an approach, but you should be careful to see what is or is not happening there. There I'm listing 3 existing solutions, where actually the second one by Bisasa and Tump is simply let's just split the vocabulary into training and test words, and they do not discuss whether the information about the test words might leak through the context and through the contextual embeddings into training words. So we suggested an improvement of the method, or let's say an alternative to the method, where we do not split the vocabulary only, but we also split the sentences into some seen and unseen sentences, so that we ensure that the test words that we test on were never seen in the training. So we test only on words which are not part of the training sentences. A problem of the method is that this means that we only test on quite rare words, because frequent words will often appear in the sentences. So our method is only a way of measuring whether the memorization problem occurs. It's not a solution of doing the probing. So that's the downside of our method. But nevertheless, we have managed to show and basically to reconfirm the results of previous authors that the memorization of word identities does occur. And we have been able to measure the effect. We have been able to see that it's much stronger with static embeddings, which encode exactly the word identity, whereas contextual embeddings are not identical for the same word in all contexts. We see that it's stronger when you have small training data, so it's easier to overfit for the classifier. And also when you have a stronger classifier, such as multi-level perceptron, then it's easy for it to memorize the word identities and the labels associated with them. So if you have just 50 sentences and you have static word embeddings and you have a strong classifier, then the difference can be quite large, so more than 20 percentage points between the words you've seen and the ones you've not seen. So you should be careful about any research which uses small data and strong classifiers and static embeddings. But when you really move to contextual embeddings, a simpler classifier like linear classifier, and you train the probing classifier on a larger data set, like 10,000 sentences, then already we've shown that the effect actually is quite small. So that was for memorization. Now I'm giving the word back to David.
Okay, thank you. So the last contribution to analysis of contextual embeddings is a work which was made by Tomasz Limisiewicz, but I will present it. So it's about separating whether we can separate the lexical and syntactic features in contextual embeddings. In the last year, there was a very good work of Hewitt and Manning, and they took the BERT contextual vectors and trained a projection matrix to obtain another vectors. So they take these contextual vectors and have this probing matrix, and they obtain another vectors, and those differences of these vectors would approximate the distances between tokens in dependency trees. So they, when they have these vectors, they can run the minimum spanning tree algorithm on such these vectors on the distances between these vectors, and they gained more than 82% accuracy on English pen tree bank, which was very good results. So they show that in the contextual vectors, they really include information about the dependencies, because you can see on this example, on one sentence, the dependencies are really good compared to the black gold dependencies. So they are almost the same, I think, in this case. So this was the work by Hewitt and Manning in 2019, and we use this approach, but instead of using only one matrix, which can be any matrix, we decompose this matrix into two matrices, into one orthogonal matrix and a diagonal matrix. And the feature of orthogonal matrix is that it only rotates the space. It doesn't change it. It only rotates the vector space. And then in the diagonal matrix is the only one vector of words, because it's diagonal. And the diagonal matrix assigns weights to individual dimensions from the rotated vector space, and tell us how important are individual dimensions for the probing task. So we probed, or Tomasz Limisiewicz probed for syntax, and the observation was that when he decomposed these two matrices into like orthogonal and a diagonal matrix, many of the numbers in diagonal matrix, weights in the diagonal matrix, were very close to zero. So we can remove all these dimensions and use only these dimensions that were not zero or not close to zero, and it worked very good even without even on this subset of dimensions. So this method showed that which dimensions of this rotated space, only this like the original space, the original contextual word embedding space was only rotated, so that individual dimensions have some features, and it shows that only which dimensions are useful for probing for syntax, for example. So the idea on that was that we could probe for more different tasks, where the shared orthogonal matrix is the same. The orthogonal matrix is shared across these tasks, and the question is, or the whether we could separate the dimensions in this diagonal probe, whether we can separate this like this useful dimensions for the specific tasks. And we ran the experiments with two tasks. One task was like predicting distances in dependency trees, so it was the syntactic task, and we added the we also probe for distances in a WordNet hyperonymic tree structure, which represents lexical features. And when we train it together, like with shared orthogonal metrics and different diagonal matrices, we observed that the syntactic and lexical, that the dimensions used for syntactic probing and for the lexical probing were very different, like almost disjoint. When we order all the dimensions, it was like almost 800 dimensional vectors. And when we order these dimensions, first according to the weights for syntactic probing, and then according to weights for lexical probing, like for the WordNet probing, we observe that these are really very well separated. Like only a couple of these blue points are here, but otherwise they are very well separated. So there are if we rotate when we rotate the space, we are able to identify syntactic and lexical dimensions of the BERT representations by only rotating the vector space, so that we need to rotate them so that to transfer the features hidden in linear combinations of dimensions into single dimensions. So see, first we have to somehow rotate it using the orthogonal matrix, and then we can easily identify the syntactic and lexical dimensions. So I think that's very good observation, and so we still have many dimensions that are not neither in syntax nor in lexical features. So we would like to know what is in the rest of the features, what can be there. So in case you have any good task, we could use for such probing. You can let us know, and we will try it. So this is a study which is currently being done by Tomasz Limisiewicz. And okay, so this was the contextual representations, contextual embeddings in a mostly transformer architectures. And let's move to the last part of this presentation, which are the self-attentions in transformer. So now you can see once more the transformer architecture. So we already talked about the word embeddings. Then we talked about the contextual embeddings, which are these ellipses. And then I'm going to talk about the self-attentions. So these are like the matrices, like the connections between the contextual representations, showing how much word representation in one layer, like the word representation is one layer, contribute to one word representation in the following layer. So these self-attentions may be visualized by such a heat map. It's a squared heat map, and each line corresponds to the distribution of words or of the contextual representation of words on one layer, how they contribute to, in this case, to the first contextual representation in the next layer. So this is the second row, how they contribute to the contextual representation to the second layer. So these are complete bipartite graphs represented by these visualization heat maps. Okay, so in this work we analyze these heat maps, and we would like to find out how much they are they represent syntactic features, because they are relations between like word embeddings, so they should be somehow parallel to the dependencies, for example, in our annotations. So in this work or in these studies, we analyze the self-attention weight matrices, and we analyze it in neural machine translation, in the encoder of the neural machine translation, and in the BERT-based model, which is a pre-trained model. So we would like to know to what extent the attentions between individual subwords correspond to syntactic features, and whether it is possible to extract syntactic structures from them. So I will show two studies. One is using transformer and neural machine translation system for extracting the phrase trees, and the other is using the BERT model for extracting the dependencies and dependency labels. So first, the phrase trees. When we visualize the self-attention heat maps from the encoder of the neural machine translation, we observe something like we call it balustrades, because it looks like the balustrade on the staircase. So we observed these like continuous segments of words attending to the same positions, which looks like syntactic phrases. That usually attends to the boundary of these phrases. So our question was whether these like these balustrades, whether these phrases, whether these are syntactic, and to what extent, and whether we can extract the phrase trees from the self-attentions of a neural machine translation, and how, if we are able to extract these phrase trees, how they differ from manually annotated phrase trees that we have from, for example, in Pen Tree Bank or Ningra Tree Bank. So yeah, we really observed such a balustrade, such a phrases in many of the attention heads in the encoder. It was about 70% of heads. It contains the visualization of 70% of heads was like these balustrades, these balustrades, like these phrases. That attends to the same word, and our approach was, okay, we used French to English, English to French, German, English, German, and six language pairs. And for machine translation, we extracted the attentions, and for each possible phrase, we assign a phrase score, which was like collected and averaged over all the heads in all the layers in the encoder of the neural machine translation system. And then we have, for each possible phrase, we have a score, and then we use the CKY algorithm to get the the tree, to find a tree with a maximum score. So this algorithm is completely linguistically uninformed. So it is like unsupervised algorithm to get a tree from the self-attentions, and we observed the trees, and we think that a lot of rather shorter phrases are well annotated, and sometimes also the clauses are in the same subtree are well annotated in these extracted trees as well. So yeah, you can view it in this. You can see it in this example. There are many phrases correctly, and so yeah, there are of course many mistakes as well. But but this is the unsupervised induction of tree. So I think this result is very good, and show us that that the emergent structures from the structures based on the attention weights are syntactic, to some extent, and then we see that they really capture well the shorter phrases, and they also very well capture the sentence clauses. So what is separated by commas or conjunctions is very well separated as well in the encoder of neural machine translation. So this is how we can get the phrase trees from neural machine translation. And the last study is about, this is also the work done by, like the joint work by Tomasz, Limisiewicz, and Rudolf, Rosa, and me. And this is how it is with self-attentions and dependency relations in the BERT model. So there are many works show that individual BERT attention heads somehow encode different or particular dependency relations. Our contributions to this is that we found that some of the heads are more abstract, and so there exist heads in the BERT, like the self-attention heads in BERT that include much more dependency relations together. Whereas there are heads that are like, on the other hand, there are heads that are more specific, like they separate one dependency relations into more subtypes, so that there are more heads that are encoding the one dependency relations, but so they somehow subcategorize these relation types into more times. And we also show methods how to extract label dependency trees from the self-attentions in BERT representations, and we get quite a 52% attachment score, which is comparable to other unsupervised system for getting syntactic dependency trees. And we also are able to predict labels, but the results are not very good. But you can see, at least on this example, that we are able to somehow get the dependencies from the, like, in unsupervised way from the BERT representations. So these are two examples of attention heads. You can see that the first head is capturing the adjective modifiers, and the second head is for objects of verbs. And yeah, the last picture I'll show you is when you do the analysis of syntax on different layers of different models, you can see how syntactic different layers in different models are. So here, so this is the picture generated by Tomáš Limisiewicz. So he shows that, for example, in BERT, the most syntactic layers are like between 6 and 8, 6 to 9, layer 6 to 9 out of 12. In the large BERT, it's like between 13 to I don't know, to 17, to 20, and these more syntactic. So these are, you can see that these are BERTs, and even the even the representation at the last layer are highly syntactic. Whereas, for example, in GPT-2 model, which is a language model that predicting the next word, you can see the highest the layers that are most syntactic are like the fourth and fifth layer. Then it goes back to the very like non-syntactic layers, and that's because I think it goes back to the words because it needs to predict the next word. So that's why the GPT-2 is like the most syntactic features are in the fourth and fifth layer. And here you can see the syntacticity of layers for neural machine translation for different language pairs, and you can see that at the end of the encoders, there is the most syntactic layers are at the end of the encoders. Only English to Russian is different. I don't know why. Okay, so this is how syntax is encoded in different layers and the different models in the different transformer models. Okay, so that was all. So I can summarize the whole our talk. That okay, we try to find the linguistic properties of different kinds in different places of neural networks solving the NLP task, and we show the advantages of unsupervised methods, which are our main goal, to use unsupervised methods, because we think that they are better to find the main features of the encoded in the networks. And we show that the word embeddings, what morphological features are captured in word embeddings. In contextual embeddings, we show how we can separate lexical and syntactic information. We showed how language is encoded in language information is encoded in the multilingual BERT. Then we showed that how we can get constituency trees from neural machine translation, and dependency trees and dependency relations from the BERT model. And yeah, I would also like to tell you that today we are finishing the book, which is called same as this presentation, Hidden in the Layers. So if you are interested in this book, in this book there are our experiments as well as the experiments of many other teams trying to interpret neural networks. So if you would like to have this book, you can get it from us as a Christmas present if you want. Okay, so that was all from me. Thank you for your attention.
Well, thank you very much for your presentation.